In this next question, we are looking at drawing Lewis structures for a series of different atoms. Again, it would be helpful to have a periodic table as we're working through this problem. As you recall, one of our basic methods for drawing Lewis structures is to find the total number of valence electrons. Arsenic, which we find below nitrogen on the periodic table, has 5 valence electrons, and bromine, which is one of the halogens, has 7 valence electrons. Since there are 3 of them, we can multiply that by 3, and we get a total of 26 valence electrons. We can do the same thing in part B for silicon tetrafluoride. Silicon has 4 valence electrons. Fluorine, again, same column as bromine, also has 7 valence electrons. So the total here is 32. And for aluminum chloride, aluminum has 3 valence electrons, plus again 7 for each of the chlorines, being in the same column as bromine and fluorine, for a total of 24 electrons. So now in each case, we're going to start by drawing the central atom. And that's easy to identify here because it's the one that we only have one of. So in part A, that's arsenic. Part B, that's silicon. And part C, that's aluminum. We can then draw bonds from that central atom to each of the other atoms. I often find at this point it's useful for us to keep a running total of how many electrons we've used. So with this first molecule, we had 26, and we've used 6, so we have 20 electrons remaining. Here we started with 32, and we've used 8, leaving us with 24. And with aluminum chloride, we started with 24, we've used 6, and that leaves us with 18. Our next step is to draw lone pairs in, and we do this on all of the non-central atoms, and we put as many lone pairs as we need to give each of them an octet. Now in every case, the bromines, the fluorines, and the chlorines all have 2 electrons from the bond, and so they can each use 3 lone pairs. Here we've used now an additional 18 electrons, and we're left with 2. We'll do the same thing with each of these fluorines. Each fluorine took 6 lone pairs, or 3 lone pairs, or 6 electrons, for a total of 24, which leaves us with 0. And down here, each of the chlorines can use 3 lone pairs, for a total of 18 electrons, which leaves us with 0. So now each of our non-central atoms has an octet. We need to take another look at the central atom. In the first molecule, the arsenic has 3 total bonds for 6 electrons, and we have 2 electrons left. So these 2 electrons can go as a lone pair on the central atom. We've now used all of our valence electrons, and all 4 atoms have an octet, so we're finished. In part B, we have no electrons left, but the central silicon already has 4 bonds to it, or a total of 8 electrons, so it's happy, and we're done there. Part C is the most challenging of these three, because we don't have any electrons left, but the aluminum only has 6 electrons. Now, normally in this situation, we would take one of the lone pairs from one of the chlorines and make a double bond. But because aluminum is in group 13, we know that elements in that group are an exception to the octet rule and are often found with only 6 total electrons. Since aluminum is one of those elements, it does have 6 electrons from the 3 bonds to each of the chlorines. It's actually in its stable form, and we don't have to add anything further.